Hey everyone, this video clearly covers a demonstration on a research project that I took up as a part of my capstone project in the final semester. So I took this project under the supervision of my mentor, Dr. Shashidhar, and my HOD, Deepak Garg. So this video basically demonstrates this project as in a brief about and gives us a brief about how blockchain can be used as a service for software defined networks. So, SDN or software defined network technology is one of the most popularly accepted programmable and adaptable kind of network architecture topology, which is highly used in today's dynamic application development. So, uh, but so SDN basically involves a three-layer structure, which consists of a control panel, an application layer, and the business logic layer. So it is a programmable network and provides lots of advantages and find its application in multiple fields, sectors, and domains, such as IoT, cloud, 5G networking, and a lot of the fields. But due to its centralized architecture, it is vulnerable to a lot of attacks and failures. So some of these attacks and some of the most common attacks that SDN is vulnerable to are DDoS attack, impersonation attack, man in the middle, ARP poisoning, and traffic sniffing. So these are some of the most common attacks that SDN architecture today faces. So in this video, I'll demonstrate a proposed architecture of my own, how blockchain can be used and embedded in SDN existing topologies so that this problem can be resolved to a greater extent. These covers the project timelines that I used as a part of my research project. So what I have used in my project is basically so for OS you can use any OS like Linux, Windows, or above, but Mac OS is not compatible with the simulation tool that I used, that is OMNet++ over here. So the frameworks that I used involve INET, which is basically a topology, a networking framework, and Nita is a attack-based framework which is used to simulate DOS attacks, man-in-the-middle attacks, and impersonation attacks. So as I was saying, that SDN architecture consists of a three-layer model, which basically consists of an application layer, a control layer, and an infrastructure layer. So the construction of SDN has to deal with a variety of gaps and weaknesses, which makes us vulnerable. And this vulnerability exists in between the control layer and the infrastructure layer, which is mostly prone to different types of these attacks. So these are some of the common attack models which we can find and we come across when I talk about this project. So consider a scenario where we need to send certain data packets from an IP address of a John to Linda. So as a part of this process, the attacker, so there's an attacker who tries to initiate an ARP request and tries to impose itself as Linda for John and as John for Linda. So that is done through the IP MAC pairing, and so the attacker basically, so MAC address is basically the hardware address. So the attacker can't change that address while imposing himself as both of them. But the IP address he can falsely manipulate, and as a part of that, he can eventually gain access to both of their systems, or any exchange of data that takes place between them passes through the attacker now. So in this way, the ARP tables that stores the IP MAC pairing and verifies the IP MAC pairing before receiving or sending packets get poised. So now any communication between John and Linda is going through the attackers. With blockchain in this scenario, when I say the compromised host sends the ARP request, and then it is sent to various hosts as well as the controller itself. So the part of the controller is to basically send and operate the receival and sending of the data packets. So with blockchain in its play, the host checks whether the request is real or not using the blockchain scheme on the basis of the basis of stored previous values in the ARP tables. And so since the previous values that are stored are authentic in nature, and so they have to be real, that's why they've been stored previously. And the MAC address, the IP MAC pairing doesn't justify the new one when the attacker imposes himself to be the one. So host immediately rejects the block. So the IP MAC the IP MAC pairing is wrongly reflected in the ARP request. So the block is not accepted to be validated, and hence the transaction gets cancelled, and thus ARP poisoning doesn't take place.
Now let's go on to the proposed architecture that I said. So here, as we can see, this is a rough diagram that I made for my research purpose only. So over here you can see the blockchain being involved between the two main layers of the SDN architecture, that is the control layer and the infrastructure layer. So with blockchain in its play, this blockchain element that we add to it is basically a virtual controller that does the role play of a controller. It plays itself as a controller only, but this, like all the data requests that are sent through any switch to another switch, or any IoT device, I mean to say, like to another IoT device, so they have to first pass through the virtual controller, and then they eventually go to the SDN controller, which sends the actual requests to the designated location. So that's how the blockchain proposed architecture of this version works. And so this blockchain agenda is totally based on the block SDSec model. You can go online and read about it. For your reference, I'll also attach it in the video description below, so you can refer it. So now let's come on to the project outcomes of my research. So I came out with the solution that, as part of the project outcomes of this thesis, I'd like to say that the OMNet++ simulator has been used to conduct the experiment in a virtual environment. So initially, the two servers were deployed as hosts to generate traffic in the proposed system, and to avoid sending all traffic to the real SDN controller, the virtual controller was deployed. So, on the basis of the previously stored values in the flow table, the virtual controller uses the blockchain scheme to determine if the request is legitimate, as you can see over here also. So, this basically occurs in three phases. The so in this, like in the phase one, after passing through one of the open flow switches, the data is sent to the next level, and then the controller verifies the order and makes the open flow tables move. So the ARP tables we talk about in this blockchain reference are basically the open flow tables. They're also called the same. So in the phase 2, it sends these transactions to all the switches in the blockchain to update their individual entries until the controller flows entries have been updated. So many of the switches are modified at the same time, stopping unwanted entry from the hack switch. So during this process, the blockchain serves as an open flow entry point, you can say, or the virtual controller, you may say, it serves as the virtual blockchain based controller. You may say that it serves as the open flow entry point, and the tables are generated. So every entry in the table is also considered as a separate block, which consists of the data packets, you may say, and the timestamp and the nonce, which every blockchain node in general consists of. And that is what is sent to the open flow switches. And any sort of unauthorized entry has the ability to change it. So these are the results and experiments that I found on the basis of the SDN simulation that I proposed. So the parameters that I used to get on these results according to the block size. So the graph over here clearly shows that so I tried to find out the delay in the transaction of the packets from the host to destination, but in between the hosts. So like so what was the effective time delay that the blockchain virtual controller can cause? So that is what I tried to find out. So as over here you can see, it wasn't much, and like so this is all just on a virtual environment, but how it may work out in a practical world, so that is clearly infeasible on my part to implement that. So these were the learnings and challenges that I faced. So I had to understand how the Omnet++ tool operated and everything. So basically, this tool available online is doesn't like so they don't have the attacking packages as their updated ones. The one I'm talking about is Nita framework. So that package of them is not that updated. So even if you try on your own, you won't be able to simulate the attacks on the SDN topologies. But yes, you can go through it. You can just build your network, build your SDN network at least using the C++ uh, programming language on, and that gets stored on the system as the NED files, NED, or you can say NAD files. So coming on to the conclusion now, so we can say that due to its agile and modular nature, SDN has been implemented in a lot of real world applications. So and hence like since it's dynamic and today's app development or software development culture is also dynamic, so SDN finds its application into the roots and foundations of these structures. So security definitely becomes the prime concern over here, and since SDN works on the existing SDN topologies work on a centralized architecture, so there is a need for these packet verifications, you can say, or the a decentralized architecture to be involved eventually in this. So what I have presented in this project, in this research project, can be used for further researches clearly, and it has also been determined that blockchain offers a secure and effective way to protect the switches in the SDN architecture from the attacker. So the simulated controller also inspects the switches as they transmit the packets to ensure that the requests for flow entry updates are coming from legitimate switches. Each block in the blockchain is also modified, forwarded to the actual controller until it has been tested. So this basically sums up it. You can go on to my GitHub link attached in the video below in the description, and you can go through the blog link also to refer more about it, and feel free to hit me up on the given mail ID below if you want to know more about my research on this. Thank you and have a good day.